All right, so last time we talked about what makes Go, well, Go, what gives it that special sauce. Today, we're going a level deeper. We're getting into the absolute fundamentals, how Go handles its data. Think of it as the DNA of every Go program. This is the stuff that makes your code clear, strong, and predictable. And really, it all comes down to three key building blocks: types, variables, and constants. Now, getting a handle on these isn't just about memorizing some rules. It's about really understanding the why behind them, the philosophy that makes Go feel so safe and predictable right from the get-go. This quote right here, it's everything. You know, in a lot of other languages, a type is kind of like a friendly suggestion, but not in Go. Oh no, in Go, a type is a hard and fast guarantee. It's not the language trying to box you in. Think of it more like a contract you make with the compiler, a promise that helps you wipe out a whole category of nasty bugs before you even hit run. Okay, so let's kick things off with the most basic piece of the puzzle, the variable. It's where we store our data. And you'll see right away that Go's approach is all about being simple and safe. So you've got two main ways to do this. First up is the var keyword. This is your classic, explicit way of doing things. It's super clear and it's great for when you might not have a value for it just yet. Then, when you're inside a function, you've got this slick shorthand, the colon equals, colon equals. This is basically you telling Go, hey, here's a value. You're smart, you figure out the type. It's short, sweet, and you'll see it everywhere. Okay, but what happens if you declare a variable but don't actually give it a value, right? In a lot of languages, that's a recipe for disaster. The variable could be holding onto some random piece of memory junk, which leads to all sorts of weird bugs. But Go has a really elegant solution for this. It's called the zero value.
And it's exactly what it sounds like. Every single variable in Go starts from 0. Literally. Declare an integer, it starts as 0. A string, it's an empty string. A Boolean, you guessed it, false. It's such a simple but brilliant idea because it means your variables always start in a predictable state. You never have to worry about uninitialized variables because they just don't exist in Go.
And, it's not just how you declare a variable, but where. Go is lexically scoped, which is a fancy way of saying a variable only lives inside the set of curly braces where you create it. This can lead to something called shadowing, where you declare a new variable with the same name inside an inner scope. Now, sometimes that's what you want, but it can be a real gotcha. You think you're changing the outer variable, but you're actually just fiddling with the new inner one. So just something to be mindful of. All right, so we've talked about variables, which can change. Now let's flip the coin and talk about their immutable cousins, constants. A constant is exactly that, constant. You declare it with the const keyword, and you're making a promise that this value will never change. It's perfect for stuff like pi or a version number or some setting that's baked into your app. And trust me, the compiler will hold you to that promise. But what if you need a whole bunch of related constants, like days of the week or something? Do you have to number them all by hand? Nope. Go has this really neat little feature called iota that makes creating these kinds of sequences or enumerations super easy. It's so simple. Inside a const block, iota just starts at 0. The next constant in the block gets 1, the next gets 2, and so on. It just auto-increments for you. It's a super clean way to define a whole set of related numbers without the tedious manual work. Okay, so we know how to store data. Now let's look at what kind of data Go can work with. It's time for a quick tour of Go's built-in types. When it comes to numbers, Go gives you a lot to choose from. You've got integers of all different sizes, both signed and unsigned, so you can be really efficient with your memory. Of course, they're your standard floating point numbers, and, kind of a cool one, Go even has built-in support for complex numbers. That's a little nod to its heritage in systems programming. Next up, Booleans, the bool type. It's about as simple as it gets. It's either true or it's false. That's it. But this little type is the backbone of all the decision-making in your code. All your if statements and loops run on this. Now, strings in Go are really interesting. They are immutable, and that's a super important word here. It means once a string is created, you cannot change it, period. If you think you're changing a string, what you're actually doing is creating a whole new one. This sounds like a limitation, but it's a huge safety feature, especially when you have multiple things happening at once. You can pass a string around and know with 100% certainty that nothing is going to mess with it.
Okay, but what about characters that aren't in the English alphabet? You know, like an emoji or characters from other languages?
That's where the rune type comes in. A rune is really just a number, an int32 under the hood, but it represents a single Unicode character. This is Go's secret weapon for handling international text flawlessly. So yeah, your Go apps can handle rocket ship emojis right out of the box. And when you're actually writing a string in your code, you've got two flavors. You can use double quotes. These are interpreted strings, meaning they'll understand special things like /n for a new line. Or you can use backticks. These create raw string literals, and they take everything you put inside them literally. No escaping, nothing. This is a lifesaver for things like multi-line text or regular expressions where you have a ton of backslashes. So let's say you have an integer, but you need it to be a float. How does that work? Well, remember Go's strictness? It comes right back here. Go will not automatically convert types for you, even if it seems obvious. You have to do it yourself, explicitly. You literally have to write out the new type you want, followed by the variable in parentheses. To Go, an int and an int32 are different beasts, and it makes you be clear about what you're doing. And really, that brings us right back to where we started. That type safety isn't a restriction, it's a promise. Having to be so explicit isn't a hassle, it's a feature. It makes you think about your data and prevents those sneaky, hard-to-find bugs that pop up when the language tries to be helpful and converts things for you behind your back. So when you step back and look at all this, the zero values, the explicit conversions, the immutability, a clear picture starts to form. Go's whole philosophy is to be simple, but never, ever vague. So let's just nail down the key takeaways. 1. Strict typing crushes bugs before they happen. 2. Zero values mean you always have a predictable state. And 3. Explicit conversions force you to be clear. This deliberate design makes your code incredibly robust and easy to reason about. So take a moment to think about it. How do all these rules, this focus on strictness, on safe defaults, on being explicit, how does that actually change the way you'd build a big, complex application? Well, it encourages a certain mindset, doesn't it? It pushes you towards writing code that's clear and solid, right from the very foundation. Getting these fundamentals down is absolutely the key to really getting Go. Now we know how to handle individual bits of data, so the next logical question is, how do we start grouping them together into more complex, useful structures? And that's exactly where we're headed next. We'll be diving into arrays, slices, maps, and structs. These are the real workhorses you'll be using to build actual Go applications. I hope you'll join me for that one. This is Developer Roadmaps. Map your path, build your career.